Yes, you're most welcome, all dear viewers. As and so, the teacher, as usual, I'm still available to take you through what we are going to look at today. But before we continue, don't forget to subscribe, share, like. You'll be able to get us. As and so, in association with HD Productions in Uganda, we are available to give you what we call the best. Don't forget to subscribe. If you want to get us, you can pass 0758876705. Send a WhatsApp message on it or a call. Or you can also use 0762258869. You can reach us. You can also send us an email. You can pass via our email, that is dixocasan07@gmail.com. You'll be able to get us and will always be back. Subscribe for you to be able to get each and every update that we shall be always uploading. So let us look at this. Today we are in chemistry. We are in chemistry, and the major concept that we are interested in today is what we are calling radioactivity. But when you talk about radioactivity, as you know, there are very many concepts that you need to talk about when it reaches radioactivity. But simply we talk about the spontaneous disintegration. We can talk about the form of nuclei with emission of radiation. The radiation we talk about, those alpha particles, beta particles, and gamma rays. Those are the radiations that we are talking about. So, spontaneous, you know what it means? Someone can just think about without use of what? Energy. The spontaneous. The free energy disintegration of a stable nucleus. We are talking about the free energy disintegration of unstable nucleus with emission of radiations. Those are alpha, beta, and gamma rays. That's what we are talking about. But when radioactivity is taking place, there are very many things that happen. When radioactive decay is taking place, there are very many things that happen. In that case, we shall get some factor that we are interested in. One of them is the speed at which the sample is decaying per time. The speed at which the sample is decaying per time, we shall determine to be what we are calling the rate of radioactivity, or the rate of radioactive decay, or the decay rate. That is one. You must know that. Then you can also talk about the proportionality. We always talk about the proportionality constant rate. That case. So in that case, we shall talk about what we are calling the decay constant. Always those things you must know. Those factors, that proportionality factor, the one we are calling the decay constant. You must be able to get them through different varieties. It can be through graphical approach. It can be just by calculation, timing, among others. The applications of radioactivity, you must know them. But before today, let us look at the integral part of it. We shall integrate. Then later, we shall know how to use those integrated equations when it comes to graph work, and also when it comes to calculations. We must know how to use all of them for you to be well conversant with the concept in this case. There are very many graphs, but the issue is just using some mathematical concepts to know this concept here. Today, let us look at a certain sample that is going to decay. Let us assume that we have a certain sample of initial mass, the one we shall call N. Let N naught be the mass, initial mass of the sample, and N the remaining mass. N is being the remaining mass, then N naught is the initial mass. So we are saying, what do we mean by the word, what do we mean by initial mass? We are saying that what we have before radioactivity starts, what we have before decay starts, what we have at time t equals 0, before you start counting the time. that have now started to count the time as the sample decay is what we are calling the initial mass, N naught. Then N is what we are remaining with at any time. At any time. What you measure at is after you have finished, you have started counting, then what you have at N, we are taking it to be what? To be N. Now, when it comes to the rate of decay, decaying, the sample is doing what? Is decreasing. So we are saying that we are remaining with N at any time t, and what are we saying? The rate of decay is always equal to the change, we shall call the change in the amount that we have, or the mass that we have at a certain time t, over the change in time. Since this is decay, we shall take it to be negative. Since it is decay, it is decreasing. What you should know that there is something very small that you should know that when we are talking about radioactivity case, for people who look at chemical kinetics, you realize that these reactions, the nuclear reactions, are first order reactions. So when decay takes, this is a first order reaction. When someone asks you that, it is a first order reaction. Order one like this. So this is the reaction. So we are saying that what does it depend on? As the sample is decreasing, it depends on the amount that we have at that particular time. To decrease, like for example, look at inside your stomach, as you introduce food inside the stomach, the amount of the enzymes that will be provided inside there to work on that particular food depends on the amount of food available. If you eat a lot, it means that many enzymes will come and work on that food. But if you just put there something small, still very few enzymes will come and work on that food there. No, this scenario is different from human beings, whereby you are given just small food and about 100 people come to eat the same food. No, we are not talking about the nature of human beings outside here. We are talking about other organisms that understand the situation. So you have been given a little, it means that you provide little. You have a lot of work. For example, you have a large place to be considered when it comes to working. It means that you have to provide more workers. So we are saying that the decay will depend on the amount available. So what does it mean? The larger the mass, the higher the rate of decay. The larger the mass, the higher the rate of decay. So we are saying that when it comes to the change in this, the rate of decay is always directly proportional to the amount or the mass that is remaining at that particular time. The rate of decay is directly proportional to the amount that is remaining or the mass that is remaining at that particular time. So when you remove the proportionality constant according to the people of mathematics, what do? You remove the proportionality sign and you introduce the proportionality constant. So we are saying equals negative. Here we are talking about decay. The sample is decreasing. So if the sample is decreasing, we shall use a negative to represent that. So we shall say that now the rate of, we can use lambda that means the proportionality constant, and this is A. So that's what we are having. Now this is a differential equation in mathematics. This is now a differential equation that you can be able to look at and you solve by other methods like separable. In that case, you can be able to get the solution here. Since we are people of chemistry, some of them may not be mathematicians, we can just say that when we are dealing with this, this is what we are having. You can cross multiply. When you cross multiply, negative lambda n. Then you separate the variables. Where there is the n, bring n. Where there is t, there t. The constant can be anywhere. The variables we have are, we have n and t. So those are the variables that we are having. Otherwise, that one will be what? That one will be a over n, the n, this one is equal to negative lambda dt. The next step here is to integrate both sides. So you integrate both sides. A constant can be outside the integral sign or it can be inside. Negative 1 is a constant. That's why I'm putting it, someone can leave it inside. So we are saying that when we integrate here, we are saying that this is the natural logarithm. 1 over n becomes natural logarithm of that. Then this one equals, when we integrate, there is t power 0 here. So integration, we increase the power and over that new power. In this case, we are saying a negative number. The value is t, meaning there is t to power 0. Any number to power 0 is always 1. Okay? So we are saying that any number to power 0 is always 1. So the moment you don't see t there, it means that there is t to power 0. So just know that t is there, but it has a power of 0. So you go and increase that power. C plus 1 over 0 plus 1. Then plus c. So when you reach there, what is to naturally is n equals negative lambda, then t, then plus c. This is what we are having in this case. Now people can look at this scenario, this period here in very many aspects. Now we start, as we said, initially, at the beginning, what am I having? Initially, this is at time t equals 0. Initial at time t equals 0. Which amount am I remaining with? I'm still having my initial amount. It has not started what? Decay. Still, I have my initial amount, the one I started with. So at time t equals 0, I'm still having my element. So you substitute here. Our interest is to get the value of c. That's why we substitute. So you can. Our c is equal to natural logarithm of n naught. So after getting that, you can substitute here and see. So natural logarithm of n equals negative lambda t, then plus natural logarithm of n. That's what we are having. So when you look at this one here, this one should always be in your head. It should always be in your head because you will use it to do very many things that you are interested in. Graphs can be plotted by considering those equations. That's what you should know. You should not forget that. But this equation here can be further divided into many items. Okay? So, for example, we know everyone knows that natural logarithm of n is equal to 2.303 logarithm base 10. That's natural logarithm. 2.303 logarithm base 10. That's what you get. So if you have that, what do? You can substitute where there is natural logarithm and see what you get. So this is 2.303 logarithm base 10 n equals negative lambda t plus 2.303 logarithm base 10 n. So divide all through by 2.303. So this is logarithm, then n equals negative lambda over 2.303t, then plus logarithm, the same of n. There is also this equation here that you should not forget. This one and this one, they are the same equation, but all that this is the natural logarithm. That's logarithm base a, then this is logarithm base 10. However, they are in the same format. What do you observe? That this equation here, this is the straight line of that format, and also this one is a straight line. When it comes to plotting graphs, as we shall see in that case. So that's what we are seeing in that case, and someone can be able to look at that and really appreciate. Before we go to graph work, we shall first of all look at half-life and other things. There are very many ways of dealing with these graphs. So we shall first look at half-life before we go to graph work. Those equations can be modified into many situations. as you can expect a question, or you can expect a concept of any form when it comes to plotting graphs. So at this particular moment, I want to tell people that don't miss the concept of half-life and don't miss the concept of graph. If it comes, we shall do all the possible graphs on this part here. At this particular moment, I want to wish you the best. Don't forget to subscribe, like, share. Hassan Dixoka, the teacher. You find me there. Hassan Dixoka, the teacher, on 0758876705 or 0762258869. You can be able to send me an email on dixokahassan07@gmail.com, or go to the comment section and write there something. We shall find it. We in association with XD Productions in Uganda. We wish you the best.